to derive the conservation of momentum, we first apply Newton's second law to a small fluid element. You can see the element on the right-hand side. It's the same element we used to derive the mass conservation. And you can see Newton's second law on the left-hand side. Force equals the mass times the acceleration. And this can be rewritten as density times volume times the derivative of the velocity with respect to time. And we now want to split up the force, so the left-hand side, into a volume force and a surface force, denoted by the subscript V and S. To simplify things, we now want to only consider the x direction. So we only consider the components of the forces which are into the x direction. And the volume force can now be expressed as the density times the volume times the gravitational acceleration, because we assume that nothing else but gravitation acts on our fluid element. So what we now have to discuss for the left-hand side are the surface forces. What are they? How do they look like? So let's take a closer look at those surface forces. On the right-hand side, you can see again the control element. And here I have already marked some stresses. So the forces that are acting on the surfaces can be expressed using the stresses acting on those surfaces. So each force can be calculated by looking at the stress on a given surface multiplied by the surface area itself. And this looks complicated, but it is actually quite easy. The first thing you have to know is that this tau EJ describes the stress. And the first subscript denotes the normal vector of the surface, and the second subscript denotes the direction of the stress. So let's look at those stresses right here. They all start with tau x, and then they have a second subscript. And the first subscript tells us that the normal vector of the surface the stress belongs to goes into the x direction. So it tells us that it is this surface here. And the second subscript now denotes the direction of the stress. So for the stress which is perpendicular to the area, the second subscript is also an x. For the stress that goes into the y direction on this plane, it is a y. And for the stresses in that direction, it's a z. The rest is quite similar. So we call this stresses tau xx, tau xy, tau xz. And then on the other plane, on the other area right here, which also has a normal vector which faces into x direction, we apply the same thinking we did for the derivation of the continuity equation. So the stress which is perpendicular to this area is tau xx plus the partial derivative of tau xx with respect to x multiplied by dx, because the distance from here to this area is dx. If you now look at all the surface stresses, you can do the force balance in x direction, which reads like this. The surface force into x direction is this term, and you can pretty easy see this, because if you just look at those two surfaces right here, you can see that into x direction you need to consider this stress and this stress. They go into opposite directions. They both include tau xx, so tau xx cannot play a role, but you end up with only this term here. And then you do the next two surfaces, which is this one and this one here. So also always, so you always consider opposite surfaces. And here you can see that you need to consider this part, which will just be tau yx into this direction on the bottom surface. So the tau yx cancels out, and you just have this one right here. Notice that you always have to multiply with a. So for this one here, you have to multiply this by dx dz. And this is, if you do this for all surfaces, you end up with the force balance in x direction. So let's summarize what we did so far. We started with Newton's second law, and we then decided to only look at the x direction of the formula and to divide the force into two components. The first component is the surface forces, and the second one is the volume forces. And on the right-hand side, we have nothing else but the density times the volume times the derivative of the velocity with respect to time. And we can now further simplify this equation by dividing by dx, dy, dz. So our formula looks like this. For now, we are done with the left-hand side and we take a closer look at the right-hand side. As I already mentioned, this term is the total derivative of the velocity with respect to time. And if you remember our video from the continuity equation, you might remember that the total derivative can also be written like this. And total derivative equals the partial derivative of the velocity with respect to time plus the second term, which is the convective part. If we now want to replace this term in our formula, we have to consider that we only consider the x direction. So the total derivative of the velocity with respect to time for the component or for the direction of x becomes this term. And if you now replace that in our equation, we end up with the momentum equation in x direction. And please be aware that I now rearranged the terms. So this right-hand side used to be the left-hand side. This is the forces, and the left-hand side is the part we discussed just now. So we now have to think about how to get rid of those stress tensors components, because they do not look very intuitive. We just want to get rid of them. And for this, you have to know that the right-hand side can be further transformed. I won't go into too much detail about this because this is way beyond the scope of this lecture. If we assume that our fluid is an isotropic Newtonian fluid, we can relate the stress tensor tau, which components we see here. We can relate that tensor to the viscosity and the partial derivatives of the velocity. And it is important to keep in mind that normal stresses, meaning stresses that are perpendicular to a surface, can be related to pressure and normal viscous stresses. And if we do this, our formula looks a little bit different. You can see on the left-hand side, again, this is just a different notation from this here. So those two terms are completely identical. Right here, they are written for Cartesian coordinate system, and here they are written in tensor notation. We split up the stress tensor into pressure forces and viscous forces, and the volume forces are also still on the right-hand side. And if we now write this in a more common way, then our momentum conservation looks like this. We have on the left-hand side some inertial terms, and we have the pressure gradient, and we have some expression which resembles viscous forces. And then, of course, we have the volume forces, which can be different forces, but for now we only consider gravity. So the equations you can see right here are the mass conservation and the momentum conservation in tensor notation, and together these two equations are the Navier-Stokes equations. Sometimes the energy conservation is also included in the Navier-Stokes equations, especially when thermal effects are considered. But historically, if you're talking about the Navier-Stokes equations, you mean the mass conservation and the momentum conservation and not the energy conservation. Then again, some remarks on those equations. And the first thing I want you to remember is that the gradient looks different depending on the used coordinate system. We already discussed this in the first video, so please keep in mind that this is a tensor notation. And if you translate this notation into your coordinate system, it looks, of course, different. Then this is not the most simplified form of the Navier-Stokes equation. You can see that we still have the density and the viscosity inside the differential operators. So it can be further, or the Navier-Stokes equations can be further simplified by assuming an incompressible Newtonian fluid, meaning that the density and the viscosity are constant. And then you can further simplify this by just put the density and the viscosity outside of the differential operators. I already told you that if you consider thermal problems, you need to take the energy equation into account, but for most of the time, this is not relevant. And then you have all kind of different volume forces. So far we only discussed the gravity, which looks like this, but you can have, for example, a centrifugal force, which would look like this, or an electrostatic force, which would look like this. So some of these forces will be discussed in more detail in later lectures of this course.